We have seen how to create lists of data using our self-referential data definition. We say that a list of numbers is either the empty list or a cons pair of a value and another list. We can use this to chain together list elements into a list. The empty list is empty, but more interesting is a non-empty list like cons 5, cons 10, cons 7. Empty. But this idea can go further. What if we had an element with two self-references? To capture this curious idea, we need to make a more complicated version of cons known as a node. But first, we'll define a new itemization. A binary tree is either false or make node of anything with a binary tree and a binary tree. Now we need to define our node struct, which replaces the cons. So we define a struct node as having a value, a left, and a right. We'll explain this thusly. A node is a make node where we've got any, a binary tree, and a binary tree, just like we said before. And the fields are any type of value, so some data, perhaps a number or a string or a struct or something, maybe another list, who knows. And a binary tree on the left is the left child of this node. Notice the terminology here that we're calling it a child. And the binary tree of the right is the right child of this node. The left and right child of the node are both binary trees, similar to how our cons had a list as its second argument. But now it's like we have two lists going in different directions. We're going to need a new template. So we'll say that we define, in fact, let's write this way, btFun, a function that consumes a binary tree, bt standing for binary tree. We'll need to use the itemization template because we've got a itemization. It's either false or a node. So we ask, is it false? If so, we'll do something. Otherwise, is it a node? If so, then we'll do something more specific, because we know that we'll need to do something with the node's value, and we'll need to recurse. But instead of recursing once like we do for lists, we recurse twice. Pretty weird. So we recurse for the left, and we recurse for the right. And we'll comment out our template. I said the binary tree above could use the any type, but usually we want it to have a concrete type. Let's say we're making a binary tree of numbers. We'll need to adjust our definition for a binary tree just very slightly. Binary tree of numbers is either false, as we said before, or a make node number binary tree. I want you to know that we could swap out the numbers for strings or structs or whatever we wanted when we're making this more concrete definition. It doesn't have to be numbers, but numbers are a good starting point. Now, down here I have a picture of a binary tree. Notice that we see our number 45 is the bottom of the tree, and it has a left and a right node, 32 and 27 respectively. 32 is also a binary tree. It has a left node and then a false for the right node. 27 is also a binary tree. On the left side we have a 7, and the right side we have a 16. 15, 7, and 16 are all binary trees themselves, but they have false as both of their left and right children. Let's turn this into some actual code using our definition. So we define a number tree as being a make node. That's always the definition of a tree, is it's either false or make node. Can't be false in this case. And the make node at the base is 45. And it has to have two children, something and something. The first one is another make node. This time we'll focus on the 32, the left side. And it's got two children itself. ... The first child is a make node for 15. And 15 is itself a binary tree, but it has no children, so that's pretty simple. 32's right child is a empty tree, so it's false. So now we've completed the entire right side of the left side of the tree. Finishing up the right side of the tree, we make a node, 27, and it has a node on the left, that's 7, and a node on the right, that's 16. So we then finish everything else off, and we have our number tree all ready to go.